Hello everyone, I am Soyoung Yoon from Seoul National University and I'll present our ACL 2025 work, RoToR Towards More Reliable Responses for Order Invariant Inputs. This is a joint effort with Seoul National University and colleagues at Channel Talk. The key theme is positional robustness. How can we keep large language models reliable when the order of parallel segments, rows, choices, facts should not matter? I will structure the talk in 4 parts. First, the positional bias problem and why list-wise inputs are tricky. Second, limitations of prior zero-shot methods. Third, the contributions of RoToR, a lightweight, globally ordered circular positional ID scheme and selective routing for hybrid inputs. And finally, extensive experience on 3 benchmarks plus efficiency analysis. The take-home message is that RoToR achieves SOTA robustness on various benchmarks with lower flops. Let's start with the motivation. Lost in the middle shows that when you insert the relevant passage at different positions, GPT class models deteriorate heavily. Similarly, when we ask an LLM to be a judge, it chooses the first answer 75% of the time, a so-called first choice bias. On MMLU, simply shuffling the 4 options can reorder the model rankings by up to 8 places. The example figure on the upper right illustrates how the same red fruit question flips from correct to wrong purely by optional order. For inputs where the ordering of segments is semantically irrelevant for what we call list-wise inputs, we require the model to produce identical predictions under any permutation without fine-tuning and with minimal computational overhead. Zero-shot order invariant language models has been proposed, such as PCW, set-based prompting, or PINE, but they break in 2 ways. PCW and set-based prompting enforce invariance by isolating segments. This removes intersegment attention and degrades accuracy. PINE retains attention but recomputes a query-specific position map, incurring additional big O of n-squared operations and frequent positional ID changes. Also, none of the above methods supports inputs that has both order-sensitive and order-neutral parts. For example, MMLU prompts with none of these, where the option order is important. We address both gaps. RoToR achieves invariance with a single global ordering and a circular positional ID scheme that is reused for every query. For limitation second, we propose selective routing, which compares confidence scores from the base model and its invariant variance and routes to the more reliable answer. We will first understand how PINE works and how RoToR improves upon it. PINE assigns the query segment to the end of the sequence, then orders remaining segments by similarity computed without rotary embeddings. This operation is repeated for every token, layer, and head, which amplifies out-of-distribution behavior and runtime. Specifically, PINE induces 3 problems. First, frequent alterations on positional IDs. Second, it's computationally expensive due to attention value computation without position IDs, and it's numerically unstable in case we have ties. We cannot fully guarantee invariance. RoToR removes query dependence. First, we sort segments once using a deterministic rule. Second, for every query, we rotate the global list so that the query segment is last. The internal causal order is preserved. The process avoids additional attention computation and guarantees 0 ID collisions. The illustrations show that PINE's position grids vary across heads, whereas RoToR's grid remains stable. Consequently, RoToR reduces additional computational overhead and narrows the train and test distribution gap. 3 ordering rules were evaluated. First, lexical, which hierarchically sort on tokenized ID numbers, monotype-based relevance scores, and inverse frequency IDs, all 3 outperform PINE. We use the lexical ordering as default unless stated otherwise. For hybrid tasks, we compute the max token probability P for both models. If the probability of RoToR exceeds the ones in the original plus alpha, which is 0.2, we keep RoToR's answer. Otherwise, we keep the original. We experiment with 4 benchmarks, 2 different model backbones with various model sizes, and report results on various baselines, including the original order-sensitive variant, PCW, set-based prompting, PINE, and RoToR. we will look at the efficiency gains. Relative to Pine, RoToR cuts flops by 98 to 98% on QN 72 billion and reduces the end-to-end latency by 23 to 43% on the lost in the middle benchmark. Collision rate of positional IDs is reduced from 42% to 0. On lost in the middle, RoToR Red raises the best subspan EM from 59 to 62% on Llama 8 billion and remains almost flat across all 30 passage positions, whereas the baseline blue fluctuates by up to 5 points. We observed similar trends across different QN and Llama with various model sizes on the lost in the middle benchmark. Results on RoToR remain stable and achieves better exact match scores than the baselines such as the original model or the Pine model. Results on KGQA, for example, with 50 retrieved passages, triples, RoToR improves F1 over Pine by 2.3 points on QN 7 billion and halves the standard deviation after shuffling segments compared to Pine. Gains persist across model sizes. For MMLU, RoToR alone scores lower than the original because some prompts are order sensitive. However, RoToR with selective routing restores accuracy to 68.5% on Llama 8 billion, matching the original, while maintaining invariance over various order permutations. In summary, RoToR provides a training-free computation-efficient path to order invariance in decoder-only LLMs. Selective routing extends the method to mixed input scenarios. The code and data are publicly released. This is the end of our talk, and thank you for your attention.